Oh, yeah, that's definitely a fun. Circled it, wrote a different number. Thank you, yeah. So the way that I like to deal with these table problems is I like to kind of think about sectioning off my intervals. I like to draw right on the table to see what's going on. So, I know it's on the board, but copying down the table is pretty helpful. But like on a test, on an AP exam, things like that, when you have the table right there in front of you and you can write on it, I think it's pretty helpful to kind of think, okay, my first rectangle is going to go right here, spanning between 0 and 2. It's going to go up to that middle y value, the 6. My next one is going to span these two values between 2 and 4, going up to 5. Then between 4 and 6, going up to 10. Between 6 and 8, going up to 11. So I kind of draw those rectangles out on. That's the way my brain likes to see it. So that's how I got my midpoint sum. Thoughts about that? Do we still need some time for the trapezoidal sum, or you want me to work through that?
Work through it.
All right, speaking of.
Let's go.
All right, let's take a look at our trapezoidal sum. So again, 4 equal subintervals for this trapezoidal sum. So we're going to have a trapezoid that goes between 0 and 2, between 2 and 4, between 4 and 6, between 6 and 8. We're going to still have a trapezoid go up everywhere. We would have had a rectangle with our midpoint sum. The difference is what the top of that shape looks like. So for the first one, right here, if I'm thinking trapezoid, I'm thinking about the area of a trapezoid formula. I'm following that. It's going to be 1/2. The bases are those vertical lengths, the 4 and the 3. My output at those two x values, the 0, the 2, those two outputs are the bases. So I'm doing 1/2, 4 plus 3, times the height of that trapezoid is the change in our x value. And our change of x is 2. So 1/2 base 1 plus base 2 times the height, which is really just the change in x. the next one, very similar, 1/2. It's going to be 3 plus 8 this time, times 2, because our change in x is a consistent 2 throughout all of this. 1/2 base 1 plus base 2, that's going to be 8 plus 14 times 2. And then finally, 1/2 base 1 plus base 2 is going to be 14 plus 9. Our change of x again is 2. Change of x is a consistent 2 throughout. That is the height. Now, I've had students in the past notice how much they love this particular problem right here, because notice if we're multiplying by 1/2 up here and we're multiplying by 2 back here, those are really just canceling out. And you don't have to do a lot of this math. It's really just 4 plus 3 plus 3 plus 8 plus 8 plus 6. It's kind of nice when you're doing a trapezoidal sum where the change of x is 2. You get something nice. Obviously, this doesn't always happen this way. Our change of x could be 1, it could be 3, it could be 1/2. You have to take the problem as it comes. But when we do this, 4 plus 3, this gives us 7 plus 11 plus 22 plus 23, and that'd be 30, 41, 63. So those two are very close in outcome. But the setup is the truth here. I mean, after that, it's just doing some math, and if you simplify it first, that's great. If not, then you still work it out and you can still get the right answer. Questions about our setup, how we're reading that table, anything at all here? All right, one more table problem for us. Take a look at this one right here. There's a few things that are here to try to potentially get you, not to get you, but so that we can try to think through. But first, we are trying all of our approximation techniques. So you're trying with a left Riemann sum, a right Riemann sum, a midpoint sum, and a trapezoidal sum. We're doing 3 equal subintervals from 0 to 6 with this table. So take a look at this. And I'm walking around if you have questions. Anybody notice anything tricky about this problem so far? Cool. right, seems that we're all dealing with this well, but just in case. Notice that we are only looking to approximate the area from 0 to 6, and they did give us more information than what we need. So if that has just been a complete non-issue and not a big deal for you, that's awesome. But for a lot of students, having this extra information right here in the table would be a distraction, would be something that you feel like you need to deal with. But in reality, we're only looking at t values from 0 to 6, so that's all that does matter. So as I walk around, it seems like we're dealing with that fine, but just wanted to make sure we realize that extra information, not a big deal. All right, as you finish up these, you can take a look at what I've got up here on the board. Again, small things that make this a little bit different than other problems we've seen before. We did have more information on the table than what we needed. That is a pretty common thing on like the AP exam to give you, like they might, like this right here, we've got a T value, which is commonly a term in seconds, and R is typically a rate, and we're gonna see how definite integrals interact with these things. And they might give us information for all kinds of different values of time. Like if T is representing seconds, then they might give us all the way up through T equals 10 seconds. What's going on at all these different values of time, but they might only want you to worry about the first 6 seconds. And so it is a practical thing to have a lot more information, but just answer a specific question. So that is realistic to see on the AP exam. Maybe they'll try to trick you with that, maybe they won't. It's not really trying to trick you, it's just, hey, do you know what these bounds mean? Can I confine myself to these bounds? The other thing is, there were some negative values in there. That right Riemann sum, the trapezoidal sum, both interacted with that negative output right there. And you treat it like normal. You don't get scared off by it, because we know that if we do have a negative output, or if we have part of our area goes below the x-axis, it's essentially just going to deal with itself. The area below, the area above kind of cancels out with each other when it needs to. You don't really have to concern yourself with it or scare it, just deal with it like normal. So the fact that that was -4, you just subtract 4. So thoughts, questions on how I set up any of these, how I worked out any of these? All right. So again, Riemann sum's huge. Huge, essentially, like, not completely free, but they feel like free points when this stuff comes up on our AP exam. We're going to see lots of Riemann sums come up on free response portions of the AP exam, and free response questions are worth so many points on that AP exam. We are pretty much guaranteed to have a Riemann sum on our free response question somewhere. And we'll talk about that a lot more when we get closer to May the 9th. But I want to switch gears a little bit. It's really not switching gears. You're going to see why it's not switching gears. But I want to talk about something that'll help us get a better understanding of our definite integral. We've been estimating our definite integral all week. We've been essentially understanding this a little bit more and a little bit more of what it means to be the area under the curve by estimating it in all kinds of different ways, investigating it. And I want to talk about, if I can find it here, I want to talk about a different notation entirely, but means something very much related to our definite integral. And you don't have to write all of this vocabulary associated with it if you're taking notes, but this is what we're looking at right here. We want to kind of understand some basic of this sigma notation or summation notation. This sigma symbol right here does essentially tell us to add. It tells us to do a bunch of adding. This symbol right here, we have on the bottom, we have I equals 1, and that could really be any variable on the bottom, but that is telling you essentially what value to start with. And then the number on the top is telling us what value to stop at. And then we have some kind of what's basically a function that we're inputting our starting value at. And as we input that starting value, we're going to increase until we get to that top value. And we're going to add along the way. So notice this very general form, and we're going to see some very specific examples to understand this a little bit better. But a subscript I, we're starting at I equals 1, we're going to n. So we're going to plug in a 1, so we have a of 1. Then we're going to plug in a 2, and we're going to add it. Then we're going to plug in a 3, we're going to add it. And we're going to keep plugging in a 4, a of 4, a of 5, a of 6, a of 7. We're going to keep adding all the way until we get to a of n. This idea, loosely, again, we're going to talk about it a little bit today, a little bit tomorrow. We're going to relate it to our definite integral. At the end of the day, knowing summation notation is not a big part of your AP exam. In fact, I would be very, very incredibly surprised if you see anything on your AP exam related to that sigma notation, even though understanding sigma notation is a part of our, like, the standards on the back wall for AP calculus. Rarely does this ever come up on release questions, on practice tests, things like that. But what I want to use this for is to help us to understand the definite integral, and that's why I think they have it back there. So let's just understand sigma notation a little bit better. Tomorrow we'll use it to understand definite integrals a little bit better. Let's take a look at these. Here we are summing from I equals 1 to 6. We're summing I. So that means we're going to plug in a 1. We're going to add, plugging in a 2, plugging in a 3, plugging in a 4, plugging in a 5, plugging in a, we stop at 6. Because it's just I, I'm literally just plugging in that number all the way up to 6. I don't want to, you know, we can add these 10, 15, 18, it's 21. What it sums up to be is not as important as understanding how it's working. Here, we're starting I at 0. It doesn't have to start at 1. It can start at 0. We want to go, starting at 0, we want to do I plus 1. We want to go all the way until I is 5. So we're going to have 0 plus 1. We're going to add that to 1 plus 1. We're going to add that to 2 plus 1. And then 3 plus 1. And then 4 plus 1. And then, thank goodness we made it 5 plus 1. So that's, now that my hand is done cramping, I can add these up. When I look inside each of those parentheses, notice that was just another way of writing the first one we did. It was really just 1 plus 2 plus 3 plus 4. So, just kind of showing us how sigma notation can be written slightly different to represent the same thing. Starting at I equals 0. Of I plus 1 to 5 is the same thing as starting I equals 1 of I to 6. You'll see what's going on here, adding these things. For this next one, we're doing a J. So again, showing it doesn't have to be an I as our index. It could be a J. So J, starting at 3, we're going to 7 of J squared. So that would be 3 squared plus 4 squared plus 5 squared plus 6 squared plus 7 squared. I'm going to stop adding these together because to me it's, I want you to see what's going on, but I know we could add these things up. I certainly hope we could. Next one, a little bit crazier. J going from 1 to 5. We've got 1 over the square root of J. So that means we're going to have 1 over the square root of 1 plus 1 over the square root of 2. And we're going to keep adding those until we get to our j value of 5. These last two are the most interesting. I'm going to clear off what we've done so far so I can not write them so far down here. Notice this next one, we've got a lot going on here. We've got our index is k, so we're going from k equals 1 to n of 1 over n times k squared plus 1. Wow, there's a lot going on there, okay? But moral of the story, we rewrite this term each time, but we replace k, not n, we replace k with starting at 1 and this time going to n. So how do we do this? Well, the first term is going to be 1 over n times 1 squared plus 1. Putting in a 1 for k. I'm going to have to add that to 1 over n times 2 squared plus 1. I would then have to add that to 1 over n times 3 squared plus 1. And eventually I realized, man, I'm going to be going forever until I get to n. So now that we've established a pattern that we're increasing that k value by 1, we can put a little ellipsis there and say we're going to go all the way till we get to n. Where it stops is n. We're going to stop until we get to whatever this n value is. Maybe n is 900, maybe n is 4, maybe n is infinity. I don't know. Again, just seeing how that summation leads to. Finally, we've got one, again, pretty scary looking, but if we kind of follow the rules of what we just talked about in E, let's see if this makes a little bit more sense. We've got this, this expression here, f of x of 1, that's where my I is, I'm replacing I with 1 times delta x. I'm then going to add that to f x subscript 2 of delta x. I'm going to do 3 just to establish a pattern, but eventually I know if I'm going all the way to n, I can't possibly write all those out. So I'm going to go all the way to x of n times delta x. So sometimes we have to establish a little pattern there, see what's going on. That is sigma notation right there. I fully believe that, you know, we'll talk about it a little bit tomorrow and stuff. It's not going to be a big deal in this class, but I wouldn't be surprised if that shows up in a future math class of yours at some point for some of these. Thoughts about that? All right. Tomorrow, like I said, we're going to see how this, and I'm going to let you do some practice with this tomorrow as well. And then we're going to talk about how this understanding of summing like this, and you can see how adding a bunch of things together, that's kind of what we've been doing with Riemann sums. We're going to kind of put all that stuff together a little bit, and we're going to talk about and get a big picture of our definite integral as we get, and we're like 48 hours away from the wedding, guys. The anticipation is building, it's bubbling in my chest. So I hope you're getting excited, and that's it for us today. I'm going to pause this video.